Yeah, this is about networking, and it's about C++ standard networking. So it actually looks like we might get in C++, well, maybe 29, a standard networking interface. And this talk is about how it might look like. Well, as I said, it's C++ 29, so a lot of details are still in discussion. But I thought I will show how it could work anyway. So this is me. And actually, my current project was cancelled just last week. So if you have something interesting, I might be interested in hearing about it. So networking generally automatically has to do with concurrency. Generally, you are waiting for something to come in from the network, or you have to wait until you can send something, and while you are doing that, while you are waiting, you want to do something else. So you need some kind of concurrency anyway. And sometimes you even might have multiple network interfaces, not so often with IoT, but even then it might happen. And if you want to do concurrency with synchronous networking, and synchronous networking is blocking networking, so you say, okay, read 10 bytes from the network, and then it will block until those 10 bytes arrive, the synchronous networking. And if you want to do concurrency with that, you have to start your own task or thread for each connection. And I have actually seen that. I've seen an embedded system, but running Linux, and they actually had about 30 inputs and outputs, so they actually started 30 threads and did everything blocking. You can do that. Depending on your operating system, the task switch might actually be pretty fast. Not necessarily on Linux, but on smaller systems, task switches are sometimes really fast. The problem with that is that for each task, you need your own stack. So you are typically wasting a lot of RAM. And RAM is still something that you often don't have a lot on embedded systems. So you can do that, but it's generally not a good idea. So the other option is to do asynchronous networking. And that means you say, okay, you want to read 10 bytes from that network interface, and it immediately comes back, but this request is stored somewhere. And now you want to do something whenever those 10 bytes arrive. And the classic thing is in POSIX, the select statement or poll statement. So you wait for a lot of events, and if few events arrives, then you're woken up and you get the event ID, and then you can decide what to do with that. And you can do that. It's not super nice to program with that. So there are frameworks around that. And one of the better known frameworks in the C++ world for networking is ASIO. And so that essentially says, okay, you want to read those 10 bytes, and as soon as they arrive, you want to have this callback called. So for each event, you give a callback, and that is called with the results of your request. And the C++ committee actually decided quite some time ago to use ASIO as a base for their networking TS. And that networking TS was published, I think about 17 or something like that. I don't remember exactly. However, sorry, it looks like this will not be standardized. There are still some chances that it will be standardized as an option, but the main thing that is currently discussed is not based on ASIO, but is based on so-called sender receivers. And that is what I talked last year about. So this is a generic asynchronous event model, and well, the discussion about this went in the C++ committee for more than 10 years, and because it is actually pretty tightly coupled with execution contexts. So, for example, on a server, you have multiple cores, you might even have multiple processors, you might have GPUs, you might have other accelerators for AI, for example, or whatever. And even on embedded systems, I showed last year on the Raspberry Pi Pico, you have 2 cores. So you have 2 computing resources. And those are executors, and we had several different models, and finally we decided on a compromise, which was in 2018, I think. And then some people came, well, that is all nice, but the problem with the ASIO is if you have callbacks, you need to store this callback somewhere. And as they are all different, you need to do type erasure, and that essentially means you have to do dynamic memory allocation. And dynamic memory allocation might be slow. So people came and said, well, we really don't like that, and we have a proposal where you actually can put all your stuff you want to do, including all those callbacks and so on, at compile time into something, and then just run that at runtime. So you don't need any dynamic memory allocation, and it's, to be honest, it's very complicated. And whenever you do something wrong, you get error messages that single error messages is sometimes several thousand lines, because everything is done at at compile time. So the way it is coded is in terms of types. So you have a template inside 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 a template, and that sometimes 20 levels deep. And deciphering such error messages is not very easy. But anyway, it will quite probably be standardized, and it will probably be in C++26. So now we have a networking proposal that is based on this sender receiver. I talked about the details of, before that. Of course, we also have coroutines. Since C++20, we have coroutines, and that, of course, is also an option for asynchronicity. And so ASIO had support for coroutines, and sender receiver automatically can work with coroutines as well. So, and then that is actually the nice way to do the actual programming. Not all the background libraries, but the actual programming looks actually pretty nice with coroutines, and I will show that later. So, just a very short recap about sender receivers. So the general idea, as I said, is you put together your work at compile time. So what you do here is essentially you put together an object of some type that is determined at compile time, but it's a concept sender, and in this case it's a chain of events that should happen. So the first just produces the number 3, an integer, then you switch to another execution context, and then on that you do 2 computations, those transforms, and then you switch again to another execution context, and then you say, okay, should there have been any error? Well, with our computation there shouldn't be an error, but anyway, should there be any error, then always just return the number 3. And that's it. Now everything here to do is encode it at compile time into this object S. And now at runtime I can start that. Well, the most boring thing is just run it and wait for it, which would be the sync wait. And that actually runs on the current thread or on the current execution agent and produces the 3 on this execution agent, but then it transfers the work to some other thread or whatever this scheduler 1 is. So that's the general idea. You can chain your operations, and well, these are actually pretty boring things. That is not something you do in practice, but this could be something like wait for a network packet to arrive. So this is the idea. So all these things could be asynchronous, so you wait for something, and only if that happens, you continue with the next. So the whole idea of the sender-receiver is to provide something like an asynchronous STL. So you have senders, and those store the work that has to be done. Receivers, and actually this is a sender. This is also a sender because its result is sent to the next step. And then there are the receivers. Those provide the interface to store the result. So this actually has a receiver side, which is an incoming thing, and then it has a sender side, which is an outgoing thing. And factories, they only provide senders. So this is a factory. It doesn't accept anything, but it produces something. And consumers, those only consume something. They only provide the receiver, and this sync wait, that is a consumer in our case. And then there are the algorithms, or sometimes called adapters, which are all the things in the middle. So they accept something and produce something. So that's the basic idea. And if you are sorry, if you have an event-driven system, events are just senders, and handlers are receivers. And everything works on some execution context. And for networking, there will be a standard execution context, I/O context, which is just the current thread. So everything that you run runs on the current thread, but you can also have another thread or another core or whatever. So in this case, we have an execution context in C++ OS. You get a scheduler here, which automatically creates for this specific execution context, it creates a new task with a stack, and in this case, the stack size is 300 bytes. And so on this scheduler, on this task, you do first an async wait on a timer of 200 milliseconds. And when that is done, so when the wait is over, then we just send a heartbeat. So this work is our sender with both steps combined. And then, fortunately, there is not only sync wait, but there are others. So this repeat effect actually just starts the sender again as soon as the previous one has finished. So this is essentially just an endless loop. But again, it's only a sender, and then I just start it. And that's it. And this is the thing I showed last year. It's essentially still the same hardware. So it's a Raspberry Pico Y, Pico W, and it receives some sound, you cannot really call it music, from the network, and that is coded. It might be MP3. I use Opus. Then on the other core, we do all the decoding because it takes a lot of computation, and then we send it back to core 0, and then we have PCM data, and that can be put out using I2S. So we have two queues in between. The first one is the wire queue with the packets from the network, and the other one is the PCM queue with the decoded packets. And it could look somehow like this. And if you look a little bit closer, you will actually find a lot of syntax errors and things like that. I never run that through a compiler because it's not a good idea anyway. But it could look like this. So you have a factory that just reads data packets from the network, and then you you push it into a queue. And then you want to go to the other core. So transfer and on are more or less the same. On the other core, you do a pop from the queue. Then you do the decode. And the result is pushed onto the next queue, the PCM queue. And then we transfer back to the I/O core. And there we pop the PCM packet and send it to I2S. So I said I never compile that because it's not a good idea. And the reason why it's not a good idea is this is the work for one packet. And if I now use repeat effect, then it will only start the next read packet when I have put out the first PCM packet to I2S, and of course that is way too late. And that is the reason why I have the queues to have some buffer. So it's not a good idea to implement it that way. But in theory you could do. So actually, I said I want to talk about the networking, and that is actually a pretty early proposal, and by Dietmar Kühl. And it is based on the networking TS, so it has the same fundamental operations and objects like the networking TS, so like ASIO. But it's based on sender-receiver. However, the details of that are still open. Right now, all the networking operations are factories. So for a read, it makes a lot of sense that it is a factory. For a write, well, that might be more useful as a consumer or as an adapter. Probably as an adapter, because you still want to do some continuation on that one. But it should get the data from some other thing. But right now, they are all factories. And so the actual programming looks pretty clumsy. But the base, of course, are networking addresses. So we have that for IPv4 and IPv6 and the combined one. And then we have sockets, and we are C++, so the sockets are templates, and they are templates on the concrete protocol. So in this case, it's IPTCP, but of course you could also have Unix domain sockets. And we have stream sockets, we have datagram sockets, and then we have special sockets for servers when you are waiting for an incoming connection. So these are acceptor sockets. So this is for listening on a TCP port. And then we have the synchronous functions, the blocking functions. Send, receive are the networking variants, so you can actually give some networking flags with that. Read some and write some are the more generic ones, so these even work on files, for example. And then, of course, you have some management like connect, bind, open, close, and things like that. And with that, well, my basic example here is TCP echo server. So whatever it receives, it will send back. So because it's a server, you need an acceptor socket, and you give the address and the port you listen to, and then you do an accept, and that returns you a stream socket. And my stream socket is typedef of this basic thing. And then I just say, okay, my client is connected. And then I have a loop here. And here I just read some bytes. Then I say, okay, I got some bytes. If I got nothing, so the network connection was closed, then I say break and say, okay, I disconnect. Otherwise, I just write it back. And if the network connection was closed, I just say, okay, I'm done with this one, but I go back to the next accept. And to be honest, it worked when I wrote it, but then I wrote several other programs, and the final one didn't work, and I messed with my library in the background, so this one right now doesn't work. Sorry. But the problem is not this code, it's because I messed up the backing library. But I have something that works, so I will show something. So this is a synchronous thing, but more interesting is the asynchronous. And we have the same operations, async send, async receive, and async read sum, and async write sum. And we have an async connect, and we have, which is more important, the async accept for the server. And with this, we can write the same. Well, that actually doesn't fit on a single slide. So I will go over to this one where I can fit a little bit more on it. So this is just my initialization of the Wi-Fi chip, and here I have my acceptor socket, and then I actually create senders. And as that is actually pretty complicated, I create one after the other. So first I create a sender that does the read and the write. So I read some bytes, and then I say, okay, I got some bytes, and lint is a macro, a debugging macro actually for logint. So this just gives me the number. If I got 0, I set the stop flag, and the return of that is the number of bytes I got. And so after that, I do, in this case, not a send, but a let value. The difference is very subtle and has to do with lifetimes of intermediate objects. So we have to go down and...
Yeah, sorry for not telling you in advance. Today is like National Alarm Thingy Day in Germany. So right now there's alarms going off everywhere in Germany just to figure out whether our catastrophe alarm system actually works. But it looks like it works a little bit, at least. Yeah, now everything's quiet again. That's good.
Okay.
Sorry.
Yeah. No problem. I didn't raise the alarm. And so, as I said, this let value is more or less like special then. And because my write is a factory, so it doesn't accept the sender directly, so I actually use the on and give it the scheduler, and then just the async write. So I read some bytes, put some message on the screen, and write it out. And this I/O scheduler, that is something I didn't show you yet. So this is the I/O context that comes with a networking proposal. And this, I will just try to speak loud enough against the alarm. And this I/O context is actually the current thread. So as long as I don't run this I/O context, nothing actually happens. Even if I put something there, nothing is started until I actually start this context, and this is started way down here here, this is actually the loop, this one and this one as well. This is a loop that runs all the operations that were sent to this I/O context. So, but we had this read-write. So this read-write object now has the work to read bytes and write it back, but that's all. Now we want this in a loop because we want, after we have sent something back, we want to wait for the next one. So my echo loop, that is just a repeat effect until. And again, I have to put it on my I/O scheduler, and I put the read-write on my I/O scheduler, and then I also have to give a functional, in this case just a lambda, that returns true if I want to stop. So if I want to end this loop, that is why it's not repeat effect, but repeat effect until. And this is just my stop flag. So again, this is just an object of the concept sender. And now my accept loop, that actually does an async accept on a scheduler, and then it just starts my echo loop that I have put together here. And this is not inside a loop. So after the client disconnects, it doesn't continue yet. So this is actually my running loop. So I always set my stop to false, and then I run my accept loop, and should it, I think this only runs one thing. So I have this one. This runs until there are no more operations on this I/O context. And if that's done, I just say, okay, my client said goodbye, so I start again with everything. Well, if you look at this and look, well, this start detach and this on, and so, and why do you have to do to use let value here and not then, and all this is actually pretty complicated, and to be honest, I don't really understand the details. I just, well, Dietmar has a proposal, and he also has a sample implementation, and I just looked at his examples and modeled it like those examples. So to be honest, I don't know the details why I have to do all this. And as I said, this is all pretty complicated, but you can make it simpler using coroutines. And this one kind of works, but only for one client. It doesn't really do the reaccept correctly. So I don't show this one. But instead, I just show the version with the coroutines. And that is actually, from the programming, much simpler. So again, here I have my setup. Here I have my accept socket. And now I have a coroutine. This coroutine is actually a lambda, but it is a coroutine because it returns a special type, and it has co-await on it in it. So it's compiled as a coroutine. And here, actually, it just looks very natural, I think. So you just say, well, I do a co-await for my accept. And then I say, okay, I connected my client. And then I just read some bytes, say, okay, I got some bytes, and write those bytes again, all with co-await. And while it's waiting, well, your I/O loop can do something else. And then down here, my loop looks more or less like before. No, not exactly, but more or less. And this one actually works. So I can show it. So first, because I have currently something else here, I have to download it. So this just flashes the code. And now here you can actually see it joined my Wi-Fi, and my laptop here is the access point. And now here I have a toy client, which is also by Dietmar, which is just a client, and this runs here on my laptop. So I can actually say toy client, and I have to give the IP address. So you see here that the client was connected, and now I can just send some bytes here, and this tells me I got 8 bytes. So it's 7 characters plus the line feed, and of course I can send some more. And then I can stop it, and this is also a bug in my library, but has nothing to do with the main program. So I got 0, so the first loop ended, so the client is done, but it is already waiting for the next connection. So just connect again, and just send a single byte, which comes as 2, and again some more, and then we can stop it again. So thank you. So this actually works, and as I said, the others worked at some time as well. So the actually program that I show here, that is correct, but the library has some bug right now. So there's a coroutine code. So now, last year I showed this, but last year the networking didn't work. So this year the networking works. So I have this, and the relevant stuff here for the networking, and I show only this stuff, not all the others that I have shown last year. I have a class audio player, and the constructor actually does the connect to my sound server. So the constructor starts all the Wi-Fi stuff and so on. And well, no, the Wi-Fi stuff is actually started here. But then I do the connect, and actually the startup is completely synchronous. So I do a connect and wait for it, and then I have to send some message to the server, and then I will get several messages from the server that I simply ignore because I know exactly what the server will send me from the decoding and from the coding and all this kind of stuff. So I actually read the messages here, and I first have to read the header, and the header tells me how much bytes come after that, and so here I read the rest of the message, and I just ignore everything until I get the codec header, because then I know, okay, the basic handshake is done, and so this is this one, and after that I just run the start, and this looks pretty complicated. Unfortunately, this is the version that works, and the coroutine version, that is the version that didn't work, and on trying to fix that coroutine version, I broke the library. So I have to show you this one, and it's actually a little bit more complicated as before, because I always have first to read the header, and I have to make sure that I read the whole header, because this is TCP. And so it could be that I, on the first network packet, is only the first half of the header, and only then comes the rest and things like that. And the same then for the payload. So here I set up a buffer, and this buffer is actually a special thing because it knows how much bytes are left in that buffer. So I can use the same buffer again and again until it's full. So I set up my buffer here, and then I say repeat, receive some bytes, and but it's a repeat until, so until the buffer is full. So the number of bytes that I could read into the buffer is 0, then I know the buffer is full. So this one is just the repeat effect, but after that I have the full header. And then I have to check if it's a wire chunk, then it's actually sound data, and I'm interested. If it's something else, I'm not interested, but I still have to read the data. So in the first case, I set my buffer to my chunk, and then that chunk is just a member variable, a member buffer of my object, of my audio server object. And otherwise, I have some throwaway buffer that I use for all the other stuff. So here I only set the buffer, and then I do the same as before. I do the repeat effect until, and do the receive until my buffer is full. So this is the work to read one message from the sound server. And the next one is, okay, I'm only interested in the wire chunks. So this is a repeat effect. I do my read data until I got a wire chunk. So if it's not a wire chunk, I just start the next read. If it's a wire chunk, then I go to the next and push it on my queue. And as I haven't implemented the async push yet, I just use a try push here. And I can do that endlessly. It's an embedded thing, so it just does that forever. It reads something and pushes it to the queue, and then I have my executor on the other core that reads the queue and decodes the data and sends it to I2S. But that's not so interesting here. Yeah, and then here just my data members, my socket, the header, the chunk with sound data, and this is like a span. This mutable buffer is like a span. So it could actually either point to this one or to a global buffer for discarding data. And that's essentially it. And so this should work as well. However, I still have the sound server running, just playing safe. Start it again. You don't have to read it. And so I do the programming here again. So, but by the way, I don't download the firmware for the Wi-Fi chip. I have that in Flash at a special space. Yeah, Paul? Okay. So this was done. And this is the other core, the decoder is waiting for work to do. This is more interesting. So I joined the Wi-Fi and the networking handshake is done. So now I can actually send some sound. This is just an M player that sends to the socket of the sound server. And it doesn't work. Well, trying to reboot. Okay, network handshaking done. as I said, it's not really music, it's just sound. And the reason why the sound quality is so bad is partly software and partly hardware, because this setup. But nevertheless, the networking stuff works. So for the implementation, yes, this is a Raspberry Pi Pico W, and that has a Wi-Fi modem, and that is connected via SPI. But I couldn't use the driver from the Pico SDK because the Pico SDK clashes with my C++ OS. But I found another one, this Pico Y driver, so I use that one, and then I use LWIP just for the network stack. It's not perfect, but it's easy to start. And Dietmar's CoolLib for all the networking stuff. And then I had to provide some glue for that, that it works on my C++ OS and the executors and the queue. And that's it. So you can, not right now, but in the next day, the code should be up here. And here are all the references. So this is a sender-receiver proposal. This is the old networking TS with the ACO. And this is the networking proposal. And that's it.
So are there any questions to Detlef right now?
Paul?
So one of the things I really enjoy about the synchronous receivers proposal is that you can actually use the stack and don't have to have
Exactly. Yeah.
It seems to me that you're using globals as a shorthand, at least in first. How much more difficult is it if you would want to give it buffers into the just the echo?
Well, that is actually where the let value comes from. So the let value ensures that while this let value is there, the lifetime of the things you capture somewhere, or I don't know the details, but that it lives for that. So you can create your buffer in the let value and then do everything inside of that let value. That is one option. The better option is a proposal that we still hope to get for 23 as well, which is called async scope. And that gives you something like not real dynamic memory allocation, but it's on the stack, but it let you control the lifetime. So it's kind of global, but it's on a stack. Yeah, Chris. Yes.
So I was wondering whether you put an effort into custom allocate or something like that to avoid those allocation coroutines.
Yeah, well, actually, Odin told me at some time that he really don't want the coroutines on a stack because the stack is too small. So of course, this co-sender that I use for the coroutine, that is something provided by C++ OS, and of course I have my custom allocator on that, and I just have a buffer somewhere, and it just stops everything if there is no memory anymore. However, having done that, I have noted how big those things are. So the coroutines, I didn't show the code here, but I have also coroutine code for the sound client. And there the coroutine frames were several kilobytes. So all those senders, they have a lot of information in it, and I have no idea why it takes so much. I really have to dig into that. Yeah, the point is, yeah, you as soon as you have coroutines, you need some mechanism to control the allocation. That's correct. Yeah, Odin? Sorry, my hearing right now is pretty bad. What do you mean with everything?
All the senders and receivers stuff and network.
The sender receiver, that will quite probably land in 26.
26.
Networking, quite probably not in 26. So that will probably be 29. However, just one thing, at least with 26, we will get a coroutine task.
Okay, so looking at the clock, I think we should stop here and give everybody the chance to grab a fresh coffee while we're setting up everything for the next speaker, Nicholas, who's already standing here. Thank you very much, Detlef.
Yeah.